Hello everyone, this is our third clip about fluid mechanics. This clip is about mass and weight, ideal gas law, vapor pressure, bulk modulus, and surface tension. The properties covered in this video are not as important as viscosity, so if you don't have time, just jump to the next video. All of you have taken thermodynamics here, so you shall be familiar with the first two. So we just do a quick recap now. Here are the definitions related to density, specific volume, specific weight, and specific gravity. In fact, these quantities are interrelated. If you know one of them, we can know all the other three. For example, if we know about specific gravity of mercury equals 13.55, then we can calculate density of mercury equals 13.55 times 1000 equals 13550 kg per meter cube. And we can calculate specific weight too. Gamma Hg equals 13550 times 9.81 equals 1.33 times 10 to the 5 Newton per cubic meter. We can also calculate the specific volume of mercury, that is VHG equals 1 over rho Hg equals 1 over 13550 equals. So we are done with mass and weight. Then we move on to ideal gas law. You are also familiar with ideal gas law for gases. You learned that PV equals RT. However, don't abuse PV equals RT and apply that to liquids like water, because PV equals to RT is only for the gases. For liquids like water, you shall apply the incompressible assumption. That is, the volume is invariant with pressure and temperature. We shall see why later in this video. But we note that we can write ideal gas law as P equals rho RT, because V equals to 1 over rho. We end our discussion about ideal gas law by a quick example. In this example, we have PV equals RT, and total volume equals mass times specific volume. We can find the specific volume from the ideal gas law, since P, T are given and we can find the table for R. From the table, R equals 286.9 joule per kilogram K. To do this kind of problem, I usually like to change all the units to SI units. So 20 degrees Celsius equals 20 plus 263 equals 293 K. The given pressure is already in absolute pressure, so no conversion is required. So V equals RT divided by P, and we substitute in the value 210 to the 3. So using a calculator, we find that this equals to, and we have mass equals total volume divided by specific volume, and that is 2 divided by the value that we just found, and that is. Then we move on to vapor pressure. In fact, you have learned about this property, but you are not aware of that. Vapor pressure is the pressure that is exerted by the vapor in equilibrium with its liquid or solid. It is a measure of ease of vaporization of a substance. Substances that with a high vapor pressure at low temperature are described as volatile. You can obtain the vapor pressure from a table or using PT diagram that you have learned in thermodynamics. As you recall, a typical phase diagram goes like this. To obtain the vapor pressure, we can read the edge of the vapor phase. So this is this line. We can see that as temperature increases, the pressure also increases. So you expect the vapor pressure increases as the temperature increases. We can see this is true from the table. Also, since the triple point of water is 0 degrees Celsius, 600 something Pascal, so we have this value in the 0 degrees Celsius. Also, as you all know that the boiling point of water is 100 degrees Celsius at 1 atmospheric pressure. So, of course, at 100 degrees Celsius, we have the vapor pressure equals to 1 atm. So we answer the previous question. Why can we say that the liquid can be assumed as incompressible? The answer lies in their high bulk modulus. Bulk modulus is a mechanical property possessed by all matter, and bulk modulus measures how rigid a material is under compression, like this in the figure. In solid mechanics that you are taking in this semester, you may heard of Young's modulus, Poisson ratio, and shear modulus. These are quantities that describe solids, so bulk modulus is here in the list, and it is denoted by K. For a solid, you can calculate the bulk modulus using this formula. You can also derive this formula if you are really interested. But this fluid has bulk modulus, but it is meaningless for you to define any other quantities on the table. So note this guy for liquids and gases. So we have to use the definition for calculating the bulk modulus for fluids. Its mathematical definition goes like this. It's defined as the change in pressure divided by the resulting relative decrease of the volume. Or equivalently, we have the formula on the right. For gases, the bulk modulus depends on how do you compress the gas. For example, if your thermodynamical process is isothermal. So we have ideal gas law, P equals rho RT, and T is just a constant, so it is not a function of density. And if we do a rho derivative on P, then so we have K equals rho dP d rho, and that is rho RT, and that's P. Of course, bulk modulus has same units as pressure and is given in pascals. But if the fluid is a liquid, then its bulk modulus is more or less constant. So let's do a quick example about that. In the textbook, the bulk modulus of water is K equals 2.15 gigapascal. From the definition of bulk modulus, we have K equals negative dP over dV divided by V. But this is actually an differential equation. Luckily, if we look at this differential equation carefully, then we can see that this equation is a separable ODE, since we can write this equation as negative K equals dV over V equals dP, such that is purely function of volume on the left and is purely function of pressure on the right. Then we can perform integration. The 1 and 2 denotes the initial state and final state respectively. If you still remember the integration formula, then and this guy equals the pressure difference. And we throw the K to the right hand side, plug in the values, and there is a negative sign here. So this whole thing equals, and taking the exponential, the final volume is, so a decrease in volume is, and we are done with this question. With such a high pressure, the change in volume is less than 2%, so it makes sense to assume that water is incompressible in most engineering calculations. So we move on to our final topic of today, and that is surface tension. Actually, you have encountered surface tension in everyday life. If you try to pour in water to a cup until it overflows and observe it from the sides, you will see something like this in the photo. Actually, this top part is supported by surface tension. Surface tension, which I denote it by sigma here, is the intensity of molecular attraction force per unit length at the boundary, and is given by Newton per meter. From the lecture notes, if we do a force balance with a half droplet, we find that the inner pressure is greater than the outer pressure by 2 sigma over r, and it will be 2 times larger for the bubble, so delta P equals 4 sigma divided by r. Let's do one more shape, and that's a cylinder. The jet of water here forms a cylinder, and if we draw half of it, it looks like, along these 2 lines, there are cohesion forces, that is surface tension, and we have a pressure force here. We denote this length by L. The cohesive forces add on these 2 lines, so we find that the total cohesive force is 2L times sigma, and the pressure force acts on this area, and that is given by delta P times the area here. The area here is the diameter times the length. Finally, we equate the 2 forces, and we copy each down. This cancel out, and we have delta P equals sigma divided by R. For water, sigma equals, so delta P equals R is 6 mm. The answer is 12.2 Pascal. That is not too big. Surface tension is also responsible for capillary effect. Sometimes you see water is sucked up in a tube in a small radius like this. That is capillary effect. We also have another quantity that influences capillary effect, and that is theta, the angle of contact. If the cosine of theta is negative, then the liquid is pushed down instead. This angle is a property of both the liquid and the surface, so you can make it to become the figure on the right by changing to the hydrophobic surface or changing the liquid to mercury. It is also possible to find H by force balance. The vertical component of these upward forces is given by 2 pi r sigma cosine theta, and that equals gamma pi r square h. And we cancel out all the common terms. So we have h equals 2 sigma cosine theta divided by gamma h. So we do a quick example from the book for this. We have just derived h equals 2 sigma cosine theta divided by gamma r. So r equals 2 sigma cosine theta gamma h. And we recall that gamma for water is 9.8 kilonewton per meter cube, and theta equals 0 for clean glass. Also, sigma for water equals 0.0728 Newton per meter. And we also have h equals 1 millimeter. We plug in all the values. Punch this into calculator and refine. So that is about 1.5 cm. So today we talk about some fluid properties that are less likely on exams. Specifically, we talk about how we describe mass and weight of a fluid, how to use ideal gas law, and some new things include vapor pressure, bulk modulus, and surface tension. So that's all about this tutorial. Thanks for watching. Feel free to ask us any question and give us any feedback in the comments below.